Okay everyone, so we are going to do work solution 8. It is almost 90 slides long, so it is a bit of a mammoth. So I suggest nice cup of coffee, maybe bring a sandwich, have a packed lunch. Right, so let's make a start. So the problem's already been set up for us in terms of finding the reactions. So we've got our two reactions there. We've got a UDL on top, and we've got two loads being applied from the top here. It's labelled up A to G. A letter is indicating a point of significant change. So we've got an A to B section, B to C, and now C goes all the way through to D for the UDL, but we also have this support here, so we're going to have to split that up as C to D and then D to E. Then the UDL finishes at the E position, so we then move on to F, where there's then our next load, and then finally from F to G for our final load. Things have been nicely coincidental ranged at whole numbers of distances from the x equals 0 position here, so I know that this force here will be applied at x equals 1. The start of the UDL starts at x equals 2, and it finishes what, at x equals 6. I make that, and then 6, 7, is that right? Yeah, 7. So 7 at that force there, and then overall we have a 10-meter long beam, so then our support at the end there is at 10 meters. So that's all straightforward. I hope you're enjoying your sandwich. So we are going to construct a shear force diagram and a bending moment diagram. We're going to do this in conjunction with one another as we move along. So we're going to be moving along our beam, and we're going to be trying to work out what the equation should be for the SF and for the BM when we're at a particular section. So as we're moving along our beam, well, there's also one there. So as we're moving along, we've got to create these equations. And as I create my equations, I will probably want to be substituting values for the start position and the end position, so I know how to plot them as well. So when I do my plot of Q and my plot of M, I'll have those values in the bank, as it were. So start off easy enough between section A and B. So we set up our XX line, and we'll look to the left of us. And what can we see left of us? Nothing much. There's no actual forces left of us, so that should be a straightforward section to work out. So since the shear forces is the sum of forces experienced to the left, and the U convention is if the force going upwards is positive, and if the force going downwards is negative, we can see nothing. Our Q value, our sum of forces, is going to be 0. And since we have no forces, similarly the bending moment, which we will take this to be the pivot position, the bending moment will tell us that there's no moments either. So force times when there's no force there means that we have no moments. So since there's no forces, there's going to be no moments. So the M equation will be equal to 0. So if we're going to plot this, plot the Q, we would have a flat line for the first section from A to B, and we would have M flat line in first section A to B. What about B to C? Well, B to C, we've gone past the first force on our beam, and it's a downward load, and it's going in that direction there. It's got a 20 kilonewtons force there. So what can I see left of me of my XX line? Well, I can see that there's this, and it's going down, and the U convention is as if it's going down, it's going to be negative. So the shear force experienced by this section is Q equals minus 20. Okay. The bending moment experienced is in terms of the distance x. So we need to work out how far our pivot is away from any forces of interest. And the only force of interest is this 20 kilonewtons here. So we've got distance from here to here. We know is going to be an arbitrary distance of x. And what's this distance from here to here? Well, that's 1. So the distance from here to here is going to be x take away 1. And this is why you want to write your q's out. And so all you need to do then is take your q value and multiply it by the distance. And so we've got the minus 20, we're going to drop that down, and then multiply it by the distance, x take away 1. Okay. So that's how the graph should now look for when we're in this region A to B. So first of all we'll have the Q flatlining, then it suddenly drops minus 20, and then it sort of does a step change like that. While the M diagram will be flatlining, and then when x equals 1 that will still be 0, but you can see it's giving you a negative gradient and it's going to drop downwards. So I might want to work out what those starting points and ending points for my two equations. Well, this one is minus 20, minus 20. This one requires a little bit more work, 0 and something else, minus 20. So the only thing we need to bother putting values in is going to be for this equation, because it's the only thing we've got x's there. So we're going to put the x equals 1 there, and we get 0 as we expect. And what about when we put when x equals 2? Well, put x equals 2 into the equation. So we're going to have 2 take away 1. That gives me 1. So going to give me the result of minus 20. So now we have coordinates that we can plot. And these ones, it's just straightforward. It's just going to be minus 20. It's just going to be a step change. So all throughout the range B to C, we know Q is minus 20. For M, in the range B to C, we know that M goes from 0 to minus 20. What about C to D? Well, C to D, we've now starting to go into the UDL. So I need to look left and calculate how much force I've got going left of me. Well, I know what the UDL per meter is, and I know the distance that I've gone past it. So let's first of all find out what that distance is going to be. So we're at X position. We know the start position of the UDL, so it's going to be X. Take away 2. That would be this. That would be this length here. And I also know that I've got this amount of proportion, as it were, of UDL left to me. So take my distance, multiply it by the how much UDL per meter you have. That will tell you then how much force you've got left of you. So let's see if we do that. So we're going to replace the UDL with a point on the appropriate force at the midpoint being considered. Right, so what they're talking about there. So I don't know what they're talking about there. To replace the UDL with a point load of appropriate force at the midpoint of the section being considered. Okay. Yeah, I can do that. We have x minus 2 meters of 10 times 10 kilonewtons per meter of force to the left of us, and this is going to be the applied this is applied at a distance of x minus 2 divided by 2. I'm working out the BM here, aren't I? So I don't know why we're talking about this for. So they're explaining to us how we work out the BM bit. I'm guessing the argument is in the work solution here is it's quite straightforward to work out what the SF bit is. So the FS bit is simply going to be the 10 times by the x take away 2. So that's straightforward. So what they're going on about here is they're talking about how do I work out the BM bit. Well, this is the amount of force that I've got left of me, and this is the distance to the midpoint for this amount of force that I've got left of me. So that's what they're talking about there. That's their argument they're using. So I've got now in effect a force, which I'm used to dealing with, and I've also got a distance. So notice that the force is 10 times open bracket x minus 2, and the distance is x minus 2 divided by 2, because the distance to the midpoint of this force is going to be half of this. So basically we've got 10 times x minus 2 times by x minus 2 divided by 2. Because that's my UDL value per meter. That will give me now the force, and then multiply this on, and that will give me the distance to the midpoint force. So here we've got the Q value. Okay. So do you see that you've got the SF value there? So another way of looking at it is just saying, for the SF, I do UDL x take away start point of the UDL. Okay, so that's for that. And then for the Q, and it's going to be a minus because it's going to go downwards. And for the Q, it's going to be minus 10 times by the, well, I'll do it like this, minus 10, so that's the UDL value, UDL, x take away x start point of UDL, square it and divide it by 2. That's how it works out there. So this is my complicated diagram for the CD region, and I've worked out well, I've already worked out what this one is from the previous, when I did the previous section, and then I did a little bit of work on the UDL by replacing it by an imaginary concentrated load. And that imaginary concentrated load will consist of a load which is growing with distance, and its midpoint is found by this term here. So we've got the force and we've got the distance. So for the shear diagram, we're only interested in forces. So what can we see left of us? We can see that there's a minus 20 left of us. We can see that there's going to be a minus 10 x minus 2, minus 10 open bracket x minus 2 close bracket, and that's it. Now again, you keep these nice and separate for when you'll want to drop them down into your M equation, your bending moment equation. So this is a linear expression and it needs to be evaluated for C and D. So this time I can't get away with the fact that I know what Q is throughout the range, because Q is now going to be a variable of x. So I need to put in where x equals 0, when x equals the start position of C, and when x equals the end position at D. So I need to put in those two values to find how Q varies. So I put them in. So my start position is x equals 2, so that's minus 20. That's not a surprise because that's where we ended up from our stop change last time. And then when we come to the end position, come to our first support where we're at D and x equals 4, and in that particular case we then get minus 40. What about the bending moment diagram? Well, that's all dependent on these things here. So the first thing we're going to do is take our 20, multiply it by the distance to that position. So that's x minus 1. So that's that distance from there to there. And then we're going to take our next force, which is 10 open bracket x minus 2 close bracket, and multiply the distance that it has to its midpoint, which happens to be half the distance of the UDL covered. And so since these two things are the same, we could rewrite this as 10, open bracket, x minus 2, close bracket, square it, divide it by 2, and then I could absorb the 2 into the 10. So I've done that there. So I've got an equation now for m for this particular region. Now, do you know what you want to do ideally in an exam situation? You want to learn how to use your calculator to plot these things out. If you go in your calculator and you go, I could do a separate video for this, I suppose. You press mode, and then you want to go into the table function, and you want to learn how to do that table function for these equations, and it becomes so much easier. Then we can set certain values of x, how many steps you want to do it in, and then you can plot out this quadratic for an exam type scenario. So we've got a quadratic, it needs evaluating at several points. That's why it's good to learn how to do the table function on your calculator. If we take just the start points and the end points, it's not going to give us enough information. But let's find what these are. So we're going to substitute in x equals 2, ends up with minus 20. Actually, I'm going to do it a few points. So x equals 3, that's a minus 45. And then x equals 4, a minus 80. To be honest, that wouldn't be enough for an exam. You would need to do it maybe at least half steps to get a nice curve. What about the D to E region? Oh god, we're doing more UDL stuff here. The only problem is now this time we've got this force coming upwards. In actual fact, this force coming upwards doesn't really affect anything on top. You could, if you just want to, just carry on using your UDL as we swing, as we go through it, but we just need to remember to now incorporate the 85. So the UDL continues as before, but there's an additional 85 reaction term. So notice that all this UDL junk isn't changing. We've still got 10 times x open bracket x minus 2 close bracket. That's the amount of force I've got left to me, the UDL, and I'm still going to have a midpoint of x minus 2 divided by 2, so half the distance to get to it. But now we've got this 85. So our shear force diagram is shear force equation, will be the same, the minus 20. The minus 10, open bracket x minus 2, and we just need to plug on the 85 when we're now in the region D to E. Again, we are going to have to work out the Q value when x equals, what would it be, 4, and when x equals 6. So when x equals 4, substitute that in, we're going to ends up with a 45. And when x equals 6, we end up with 25. So that's enough data there to plot a straight line, because we can see it's just got one variable there, so that's enough data. For the bending moment diagram now, well, our UDL doesn't change. We can just carry on moving that across. But now we need to introduce the 85. The 85 is going upwards, so it's a positive moment. How far? What's the distance to get to 85? Well, that's my x distance. Let's take away its position, which is 4. So we've got 85, open brackets, x minus 4, close bracket, and that will be the m equation. So this equation really needs, because of that quadratic there, it really needs several points to be plotting to get a decent curve. So you probably want to take it in steps of about 0.5 or 0.25, those sort of numbers. They've taken it at the 4 position, the 5 position, and the 6 position. So we really would want more than this in an exam type scenario, but we can plot it to be this value when x equals 4, this value when x equals 5, and this value when x equals 6. So that's how my m is going to vary. That will give me a sense of how the curve should behave. What about we're now here? So when we're in the region that we've just gone past the UDL, something weird happens. Since we're now here, we are no longer going through the UDL, and that UDL in effect becomes as if it's just a concentrated load. So all the UDL is now included, so we can return to the assumption made when calculating the initial reactions. The UDL can be replaced by a point load representing the total force applied being applied at the midpoint. The beam is considered as the same as this. So once you've gone past your UDL, you then get rid of it and then you replace it with a concentrated load, which happens to be 40 kilonewtons in this particular case. I think this is vaguely looking like the previous example now. So the shear force diagram, it becomes straightforward. I can see a minus 20 going left of me. I can see a 85, well I was going to do the 85 first, 85 going upwards, and then, well, with the UDL, which is 10 and it's 4 meters long, overall it's going to give me minus 40 there. So the plots, the value that I want to plot for the Q graph is going to be 25. For the bending moment diagram, well, we could drop this really and just treat this as a 40. So we've got minus 40, its position of 1 meters from the start position, so it's minus 20, open bracket x minus 1. This is 40 going downwards, so we're going to have a minus, and its position we've worked out to be is 4 meters from x equals 0. So that is going to be that. And what about the 85? Well, the 85 is happens to be located at the same position, so that's going to be x minus 4 times the 85. So all we need to do now, we're going to have a linear expression, so all we need is 2 points to plot. So I can substitute in when x equals 6, and I can substitute in when x equals 7. What about when we move past FG? Well, I could be now treating this problem as if there's 3 loads being applied left of me with 1 reaction. That's quite straightforward. The shear force is going to be minus 20, minus 40, plus 85, minus 30 there. So overall I'm going to have a minus 5. The bending moment diagram is minus 20 x minus 1, minus 40 times x minus 4, plus 85 times x minus 4, minus 30 times x minus 7. So that should be a distance of 7 meters to get back to the beginning. So that's just a straightforward linear equation, just need the first one and the last one. So when x equals 7, I can plot that, and I should have m is 15, and when x equals 10, I should have m equals 0. Maybe as a final check, I want to move it all the way to the end and check my shear force is coming to a 0 value. So let's check the shear value is returned to 0. Well, previously we had a -5. If we add on the 5 at the end, we end up with Q equals 0, so that works. Okay, let's plot this graph now, and we're going to see if there's anything called a point of contraflexure. And that's where you get m equals 0 and it's gradually changing. So we might have something like, well, not like that. We might have something like a drop like that, and then maybe a quadratic there where I've got a UDL, and then maybe it going through like that and ending like that. So here you can see that the m is gradually changing and it's cutting through the axis here, the y-axis, and where m equals 0, that is called a point of contraflexure, and you have no bending, so it's a good place to locate maybe some sort of joist or something like that. So you're not going to get any bending forces. So evaluate the bending moment equation to find out where it equals 0, to find it. For that, you will normally need to know where you can see from your plot that m is changing from 0, from positive value to negative value, or negative value to positive value. So it happens to be, I think this will be when we've just gone past the UDL, but before we've hit the third, or rather the second concentrated load. So they've rearranged it and they've found out where that position is, and it turns out to be 6.4 meters from A. Okay, so the final thing to do there in this work solution is to actually plot out your Q's graphs and your M graphs, and you'll notice that in this region, well, let's get the graph. So in this region here, actually, what was it? Yeah, it's using free forces. In this region here, m is going from a positive negative, or negative positive, can't call myself, so it's doing something like that, and I am then going to set that my m equation, which I know what that m equation is in this region. I'm going to set it to, sorry, it's going to be here, sorry, EF. So I'm going to set my m to be 0 and then find out when x equals what the x value is at that point, and that point is called the point of contraflexure.